Given a string and an array of equal-length words. Find every contiguous substring that uses each word exactly once in any order, concatenated with no gaps. Return all starting indices of those substrings. Example 1. At index 0, bar foo splits into bar and foo, both words from the list. At index 9, foo bar splits into foo and bar. Starting indices 0 and 9. Example 2. No window uses each listed word exactly once in order. The output is an empty list. To solve this problem, we must first build our reference system. We create a target map to store what we need, one bar and one foo. A naive approach starts at index 0, chops out a substring of total word length, and counts its chunks inside a temporary window map. Then it shifts forward by just one character to index 1, throws everything away, and completely reparses from scratch. This constant chopping and rebuilding causes a massive performance drag. We can completely break this bottleneck. Since every word shares a fixed length of 3, we split into exactly 3 independent lanes at offsets 0, 1, and 2. Within each lane, boundaries shift strictly by chunks of 3, recycling word counts cleanly without ever rereading characters. Let's watch lane 0 execute. Our right pointer examines the first word chunk, bar, and places it in the window map. We compare this to our target ledger. We need 1 bar, and we currently have 1. Because our count is within the target requirement, this is a valuable undercount. Our matched counter increments to 1. Our right pointer jumps another 3 paces, absorbing the chunk foo. We log it into our window map. We needed 1 foo, and we just found it. That pushes our matched counter up to 2. Because matched now equals the number of words in our dictionary, we have a complete concatenated match. We harvest the left pointer's position, index 0, and lock it in our results vault. Now our right pointer advances and takes in the chunk the. We consult our target map and find that the doesn't exist anywhere in our dictionary. Because an alien word cannot form a valid concatenation, it ruins our entire window. Our left pointer instantly teleports past this invalid word, wiping our window map clean and resetting matched back to 0. With the obstacle cleared, we begin rebuilding our state. Our right pointer reads foo at index 9 and logs it into our refreshed window map. Since this is our first copy of foo in this new window, it represents valid progress under our target limit. Our matched counter ticks back up to 1. Our right pointer takes another step and absorbs another foo. We log it, but our window map now shows we possess 2 copies of foo, while our target map only allows 1. This is an overcount violation. Because we have captured an excess duplicate, this step does not increment our matched counter. Our window is now oversaturated, and we must contract from the left to clear the pressure. To resolve this overcount, our left pointer springs into action. It steps forward by a full chunk of 3, evicting the older foo from our window frame. We subtract it from our window map, dropping our count of foo back down from 2 to 1. Our overcount is cleared, our window is valid again, and our matched counter remains stable at 1. Finally, our right pointer takes its next leap and grabs bar. We add it to our window map. Since this count satisfies our target constraint, our matched scoreboard hits 2. Our window has achieved perfect convergence once again. We look down at our left pointer at index 12 and drop it into our results vault, completing our seamless sweep down lane 0. We begin our solution scene by capturing our reference constraints. We measure the static length of a single word, which is 3, and calculate our target dictionary size. We count our required frequencies, locking them away in our target ledger. We need exactly 1 bar and 1 foo. To process our chunks cleanly without checking characters one by one, we kick off our interleaving loop. We spin up separate lanes for each starting offset. Focusing on lane 0, our left pin snaps to the beginning, and we clear out our window tracking board and matched word counter for a fresh run. Now we launch our outer sliding window loop, initializing our right pointer to start exactly where our left pointer is resting. The loop will step forward in fixed increments of our word length, which is 3. Our right pointer captures the very first chunk from index 0 to 3, which is bar, and logs it into our window board. Since we need 1 bar and currently have 1, this is a valid undercount, so we increment our matched counter to 1. The right pointer leaps forward by another block of 3, ingesting foo. We log it and check our target ledger. We need 1 foo and now possess 1, so our matched counter ticks up to 2. Because our matched count now perfectly equals the number of words required, we have hit a complete concatenation match. We harvest our left pointer's position, index 0, and log it into our results. Next, our right pointer hits index 6, absorbing the block the. We check our target map and find that the is missing entirely from our dictionary. Because an alien word can never be a part of a valid combination, it completely spoils our entire track. We instantly teleport our left pointer past this obstacle, wiping our window board clean and resetting our match tracker back to 0. Moving forward past index 9, our right pointer captures another copy of foo at index 12. Our window map now shows we possess 2 copies of foo, but our target rules only allow 1. Because this is an overcount violation, our match tracker stagnates. Our window is now oversaturated, and we enter a while loop to contract from the left and handle the pressure. Inside our contraction loop, we check if the word we are evicting was actively contributing to our match criteria. We shift our left pointer forward by a full block of 3, dropping the older, trailing foo completely out of our window frame. We subtract it from our tracking board, bringing our count of foo back down from 2 to a legal value of 1. Our window is safe again, and our loop terminates. Finally, our right pointer takes its last leap and grabs bar. Our window map updates, pushing our matched scoreboard back up to 2. We have achieved perfect alignment once again. We read our left pointer's location, index 12, and deposit it into our results list, completing our seamless sweep across our independent lanes with a final answer of 0 and 12. N is the length of S, L is the word length, and W is the number of words. Time is O of N times L. We run L interleaving offset lanes, and each lane visits every word-sized chunk at most once. Space is O of W for the target and window frequency maps. The driver collects every valid concatenation start index. Build the target frequency map from words. Store the fixed word length shared by every word. Remember how many words must fit inside each window. Prepare an empty answer list. Run 1 independent lane for each starting offset. Anchor the left pointer at this offset. Reset the matched word counter. Clear the sliding window map for a fresh run. The right pointer steps forward in word length blocks. Read the next word-sized chunk from S. If the chunk belongs to our target dictionary, log it in the window map. If this copy is still within the target allowance, increment the matched counter. While the window holds too many copies of this word, read the word leaving from the left edge. Decrement its count in the window map. If the evicted word was contributing to matched, decrement matched. Advance left by 1 full word. When matched equals the required word count, record the left pointer as a valid start index. Otherwise the chunk is an alien word. Wipe the window map. Reset match to 0. And jump left past the invalid chunk. Return every harvested start index.